Hi, I'm François Lénon, PhD student in machine learning for robotic applications, and today I'm going to talk about our work, learning prohibited and authorized grasping locations from a few demonstrations, jointly done with Laurent Bimon, Eric Néry, Stéphane Thierry, and Olivier Gibaru from Lispen Laboratory at Arts et Métiers Engineering School. Before starting, we would like to thank the organizers for giving us the opportunity to present this work at the Roman conference, and we would like to thank the reviewers for the insightful comments and concerns that help us to improve the final version of this article. So the motivation of this work came from the observation that in the industrial context, pick-and-place operations done by robots are still hardly reconfigurable, especially by non-robot programmer experts. It often requires CAD models, prior databases, or simulation environments that are not always accessible. On the other hand, grasping objects often falls under the umbrella of task-oriented grasping, where different use cases are possible, such as grasping a fragile object in a safe area, or grasping a tool for a specific mean, for instance to give a wrench tool by the handle, or to perform a screwing operation. In this context, to risk grasping reconfigurations, we propose a methodology to build a fast learner neural network model from one or a few demonstrations. It predicts the grasping affordance maps. To enforce a good semantic representation of grasping location in the learned model, we propose to indicate both authorized and prohibited locations. Demonstrations can be done in several ways, like with a computer interface, but we choose to exploit finger tracking in order to benefit directly from natural human-robot interaction without any hardware intermediate. In our setting, we also suppose that objects rely on a flat surface so that they can be easily segmented from the background. Authorized and prohibited areas are stored by recording the finger coordinates. The 2D shape of the object is obtained from the binarization of the depth image provided by RGBD camera. Then demonstration labels are generated according to the following rules. Pixel corresponding to authorized area have a value of 1. Pixel corresponding to prohibited areas have a value of -1. And neutral pixels have a value of 0. Then the demonstration set is augmented by random translations, rotations, and added noise to give variability and to increase robustness. The use of a 2D shape reduces the size of the input space and contributes to fast learning and generalization abilities. If necessary, several demonstrations of the same object in different locations are collected. The neural network used is based on a classical pre-trained network, TOSNet 121 in our experiments, followed by a light CNN with only 7,000 parameters, which can be trained in a few batches. Our approach relies on a regression problem from which the network outputs values between -1 and +1. Finally, to determine the grasping parameters, we post-process the raw output. We select the highest grasping affordances pixel as a target tool center point, subjective, and with a local PCA, we determine the orientation of the gripper. Thanks to this pipeline, a specific network can be trained in less than 5 minutes with a standard powerful GPU. We have planned a series of experiments to validate our methodology for task-oriented grasping. For the first series of experiments, different objects were used to train specific networks and validate our methods. The graph on the right side shows the evolution of the grasping success rate for this object after learning from few demonstrations. We can observe that with as few as 3 demonstrations, the success rate can be equal or close to 100% on 36 trials from different positions and orientations. We also investigated experimentally the benefits of indicating both authorized and prohibited locations of grasping predictions. We show here the evolution of the grasping success rate for a socket wrench caught by the handle and for a bulb. In blue, we represented the success rate when only authorized locations are learned, and in red, when prohibited locations are added. For the wrench, the prohibited demonstrations outperform the cases where only authorized demonstrations are given. The red drop is particularly significant when only one demonstration is provided. Indeed, for the second wrench, the similarity between the handle and the head makes task-oriented grasping more difficult when only authorized areas are provided. For the light bulb, even if the success rate is high without providing prohibited locations, adding them not only improves results, also provides a much safer prediction. When no prohibited locations are given, the grasping affordance map can be inaccurate in the fragile region, resulting in values close to +1 for these undesired areas, while we would expect values closer to 0. Indicated prohibited areas, therefore, is a safety guarantee as the network is entailed to learn better representations, such that the output tend to have negative values for prohibited areas. And as a result, even if the network fails in its prediction, the bot will tend to catch an object in a neutral area rather than in the prohibited one. thus avoiding to damaging fragile objects. We conducted several other experiments to study the generalization abilities of specific networks. In this video, we show how well a specific network trained on only one reference object can cope with unseen different similar objects, here different bulbs. Same experimentation is shown for different sizes of socket ranges. If the shape is not too far from the one of the reference object, then the network is able to make good predictions leading to successful grasps. When the shape of the unseen object is too far from the reference run, we can decide to train a new specific network for this object. To conclude, in this work we show that thanks to our proposed pipeline in a relatively controlled settings, one can quickly reconfigure grasping capabilities. It learns from few data without requiring any datasets, CAD models, or simulations. The learning of prohibited areas makes this process safer, and specific networks are able to generalize grasping strategies to similar objects. Overall, our model shows a good potential for integration in an industrial context, but it remains some limitations. The use of 2D shape hinders the ability to cope with more complex environments, such as cluttered objects, for example, in a bean picking task. In addition, the semantic segmentation must still be erroneous in some cases. Detecting these cases in order to learn the right behaviors is determinal for the sustainability of the system. Eventually, this work is the first step toward a full teacher-learner interactive system between a human and a robot to perform custom tasks, but the limitation leads us to focus in future work in exploiting more perception dimension in order to deal with more complex settings. For instance, we could use the full depth map and the colored channel of the RGBD camera. Moreover, we plan to strengthen the interaction between human and robot by exploiting confidence level and continuous active learning. Thank you for your listening.